All right, thank you for joining me this afternoon for this talk on purging undefined behavior and Intel assumptions in Legacy Codebase. You'll see a little bit more what this story has to do with Intel. Some of this stuff is from a few years ago, but that's still applies. I'm Roth Michaels, Principal Software Engineer at Native Instruments. And before I begin, I want to thank a former colleague of mine, Russell McClellan, because a few years ago we co-wrote a version of this talk that I gave a variation at CVPCon, and he gave a different variation targeted at audio developers at the Audio Developers Conference in London. So even though this is a new variation I did on my own, I still wanted to thank Russell for his work with me on this a few years ago. So I work at Native Instruments. We are a audio software company making software for music production and other audio post-production, so everything from DJ applications, virtual instruments and synthesizers, software for mixing and mastering, post-production for film and television. And you see we're now actually kind of a big family of 4 different audio companies: Native Instruments, Isotope, Plugin Alliance, and Brainworks. The reason I mention this, I come from the Isotope part of the family before we all merged together. So the stories you're hearing are from the Isotope code base, but now I actually deal with 3 25 to 30-year-old legacy code bases. So I'm giving a lot of talks about legacy code over the years because of this. So like I said, we make audio software, and kind of another one of the challenges is a lot of the stuff we run are plugins and DLLs that run other people's processes. It's not a whole lot on this talk that relates to that today, but there's some funny UB stuff that sometimes happens when some other DLL has some UB, and if you put them in the right spot with us, strange stuff happens. But that's not so much the point of the talk today. And before I get going, something I kind of always like to start my talks with is kind of a call to action for other people to consider giving conference talks if you've not given one before, or maybe even starting off with a lightning talk, because those of us that you see speaking here at this conference today, some of us have been doing a lot of conference talks like myself, other people are doing it for the first time, but we are not some magical C++ folks, just some people that have something to share, so I encourage you to consider giving a talk sometime. If you ever want feedback on your proposals or other stuff, the include C++ Discord, if you're not familiar with it, has a great channel for discussing that stuff, and I'd recommend that. But let's dive into our topic for today. Before we get going, I'm just kind of curious, if anyone has any feedback, what might be wrong with this function definition here? Kind of, but actually this is a joke I made. The reason I'm talking about random numbers, I gave a talk, the first time I gave this talk, I was also giving a talk on random numbers. But the real issue with this function at first is there's no semicolon. The reason I make this joke is our tools are getting better all the time, and I remember the first time getting errors where I wasn't getting some crazy error because of, something weird down here because there's a missing semicolon up here. The compiler actually told me, oh, hey, you might be missing a semicolon here. I forget if that was a clang thing or still in the Apple GCC plus LLVM era, but a lot of what we're talking about today is how we can use tools to make our code better, and this was a nice thing that happened. But you're right, the other problem with this function is that, at least until C+26, this is undefined behavior because this unsigned x is never initialized, and so this is not a real good random number generator, even if it wasn't undefined behavior, because this is you're gonna maybe get some weird garbage out here, or as some folks might say, you're summoning nasal demons. It's a little bit of a hyperbole, but the idea is, anything can really happen when you introduce undefined behavior. There's a great talk from Chandler Carruth that talks about why nasal demons and hyperbole might not be the best way to have this conversation, but so I recommend you check this out. But a lot of my point in my talk, that part of how we made cultural changes to care about UB is actually striking fear into developers and our QAs and PMs about this topic. So with the semicolon, this is no good, and kind of to show you what's going on here is if we compile this with clang with O0 optimizations, we get some assembly like this. And this is what's happening when we're reading X. We're just reading some memory that's not initialized. And this is why sometimes people say, oh, you'll get a garbage value. And the standard says, oh, yeah, the value is indeterminate, but it's undefined behavior. And when you invoke undefined behavior, the point is that's not allowed. The compiler says, and the language assumes this never happens. And so it's allowed to generate code based on the fact that you'll never invoke undefined behavior. So since you can't invoke undefined behavior, we can't ever actually read this X. So in an optimized version, with O3, this could just get returned to an empty function that just returns, because, of course you're not going to actually execute any of this code, so you must not really need this function body because it's not real. So has anyone ever written undefined behavior on purpose? I did it many years ago. I looked at the code gen and was like, oh yeah, this works. It's doing what I said. I never had any problems with it. And many years later, I discovered maybe that was not so great. Can everyone read this cartoon, or do you need me to read it out loud for you? Let's give you a moment to read this SKCD if you've not seen it. Not about undefined behavior, but not too far away from people maybe doing it on purpose. Yeah, and this comic reminds me of a time before one of our product releases. It's not related to undefined behavior, but a strange feature we implemented many years ago that was useful and then actually annoying users. And one of the forum posters talking about our software, this guy, Dr. Driller, commented about, hey, these guys at Isotope, these guys are clearly not serious programmers if they haven't dealt with this thing. And we love this compliment because no, none of us on the team were very serious. A few other quotes that kind of is interesting in this talk. I don't know where I first heard this, so it's quoted as unknown, but C++ has enough rope to shoot yourself in the foot. If you haven't heard, there's kind of two sayings put together: enough rope to hang yourself, or, I don't know, shooting yourself in the foot is what happens when you're, I don't know, being foolish. And what will come up later is this quote from Titus Winters that I like, that software engineering is programming over time. Because we'll see sometimes undefined behavior in your code might be a sleeping dragon that is totally fine, not causing problems for years, and all of a sudden a compiler update, or you change some other code, and all of a sudden the dragon wakes up. So after that introduction, our agenda for today is we're going to give a brief overview of what undefined behavior is. We're going to talk about a few interesting bugs that can be caused by invoking undefined behavior, and then talk about the culture changes and tooling changes we made internally to try to first stop people writing it on purpose, and then also actually try to purge the undefined behavior slowly from our code base. So in talking about what undefined behavior is, there's kind of a number of different behaviors or kind of states of a C++ program. The first one is some code can be ill-formed, and that's a compiler error, and this is just not legit C++ code, you get a compiler error. There's another kind of more strange one, which is ill-formed, no diagnostic required, which means this kind of should be a compiler error. This is not legitimate C++, but the compiler is not required to emit a diagnostic. An example of this is ODR violations, where you have two definitions of the same function. Maybe the linker can tell you, maybe not, but the point is you can have a false positive for having a C++ program due to this. We're not going to talk about that too much today, but then there's also defined behavior. That's all the kind of stuff that the standard specifies that works deterministically across all platforms. There's implementation-defined behavior, where the compiler and platform can choose certain implementations. Unspecified behavior, which we're also talking the definitions about this a bit, and then undefined behavior. And in C++ 26, there's this new one, erroneous behavior. So that first slide, reading the uninitialized variable, that becomes erroneous, which still is invalid code, but no longer is kind of going to summon dragons like undefined behavior. And also, just as an aside, I do recommend this talk from Chandler and Titus called What is C++? And this is where the concept of ill-formed, no diagnostic required being a false positive compilation was the first time I heard about it. So I really like this talk, and I recommend it. So looking kind of more detail what these things are. So C++ standard describes an abstract machine that implements C++ and has these different behaviors. So the defined behavior is we can consider that the deterministic behavior of the abstract machine. So this is what will run the same regardless of what compiler or platform you're running it on. But then implementation defined and unspecified behavior are kind of non-deterministic behavior of that abstract machine, where depending on the actual physical implementation, you can have different behaviors. So with implementation defined, platforms can choose what behavior they have and must document it, like what's the size of an int or a long, or is car signed or unsigned. And then unspecified behavior is another kind of non-deterministic behavior. The standard may suggest things, but documentation is not required, but the implementation must choose something valid. And then there's undefined behavior, where the standard makes no guarantees because this is supposed to never happen. And so the compilers assume it never happens, and anything is allowed kind of if you execute this. And then we have the new erroneous behavior, which some undefined behaviors may turn into, which is this incorrect Diagnosis recommended, programs can terminate, or like I think with the undersized variable, they return some other value. But I'm not using C++ today, and we're not talking about that, so we're in the land of undefined behavior. If you want to kind of take a deep dive into it, I do recommend this Back to Basics talk from CBPCon a number of years ago that kind of gets into a lot of details about undefined behavior. And also, these are also two great articles, one by Chris Latner and one by John Regar, and reading both of these is what convinced me the times I wrote undefined behavior on purpose was an ill-advised move. And from John's article, he describes three types of functions and their relationship to undefined behavior. So type 1 functions are ones where all behavior is defined for every input. Type 2, some inputs are defined and others are not. And type 3 are functions that are just always undefined regardless of how you call them. So if we look at trying to write a safe division function for signed integers, there's a couple things that are unsafe or undefined that could happen in this function, like you can't divide by 0. That's not just C++, that's mathematically undefined. And then also because of, at least with most implementations, they're using 2's complement, you can have one more positive value than negative values, so you also have to make sure that you're not going to cause issues with that. So in this safe implementation, this is a type 1 function, so this is always going to be defined. If the inputs are going to cause some undefined behavior, we're going to just report some error. Somehow this might throw, log, do something, and we'll return 0. And then if not, we'll actually do the division. A type 2 variation would be one where we might have some asserts at compile time or preconditions, but if you call this wrong, you're going to get undefined behavior, but for most numbers, you'll get good division. And then for an example of type 3 was our random number generator from before, where no matter how you call this, this is always undefined behavior. So let's look at a couple other examples about how undefined behavior can cause strange stuff to happen when you optimize code because of the assumptions compilers make about, oh, this will never be true. So imagine this case where we have some table that stores 4 integers, and we have a function that's going to take some input and let you know whether this value exists in the table. But we have a bug, and this is actually a common mistake that people might make writing a traditional C-style for loop. Maybe this is why we should not do those if we can avoid it. But if you notice here, we're looping starting at 0 for the first index and going for I is less than or equal to size, which means that we're going to actually check one beyond the end of the array. And so on the when I equals 4, the table index with 4 is going to look beyond the end of the array, so that would be undefined behavior if we look past the end. And so when the compiler sees this, it's going to go, well, okay, we're never going to invoke undefined behavior, so it must be impossible to ever have I equal to 4. So that must mean there always must be something in the table, because if not, we would invoke undefined behavior. So the compiler can assume, well, we're never going to get to I equals 4 because that's undefined behavior, so we must find it or else we will. And so this function is actually just true always because you're never going to be able to invoke that undefined behavior. The kind of more scary one that kind of shows up sometimes is having null checks disappear. So imagine this function value or answer where you put a pointer to an integer, and if it's not null, you return the value, and if not, we return the answer to life, the universe, and everything. And at some point, somebody added some logging to tell that value as well before actually returning the value. But you notice that happens before the null check. We dereference p for the logging. And the compiler is going to see, oh, well, you're never allowed to dereference a null pointer. So at that point where we dereference p, it must not be null. So why would we check it again later? We can elide that check, and we'll always just assume we can dereference p. And so both these examples come from a nice blog I'd recommend from Raymond Chen called Undefined Behavior Can Result in Time Travel. And there's a couple other neat examples, I think, in there as well. So now to look at some of the stuff that showed up on our code base are things that work on Intel, supposedly. So this is some code related to atomic variables that, like I said, legacy code. So this predates the C++11 memory model and atomics. So you're relying on the rules of the platform for how you're supposed to do this. So we have our special atomic unsigned int that's volatile unsigned, definitely weird today. But the reason we do this is on Windows, this was the documented implementation. You use this interlock exchange function. You're supposed to use a volatile, casting it to long. It looks a bit weird, but this is how you're supposed to do it on Windows. And so that's how this was implemented. Fun fact, our code base did start as Windows only, as Winamp plugins, before we made proper desktop audio software. So that's why I think we had this nice Windows implementation. And then the read just has a comment saying that, oh yeah, the docs say we can just read from this and it will be fine. Again, this is maybe one of those Intel assumptions. And the Mac implementation, essentially we're not doing anything with this, just using the volatiles as normal. There's a bunch of comments explaining how Apple hasn't documented this, but according to developer forums, this is supposedly true. I initially thought this was an Intel assumption, but the dates on this might have been a PowerPC assumption, not clear. But again, how did this ever work? A theme of this is don't worry about it. Like trying to think about what's going on with undefined behavior and like what's actually happening. Like some of those examples I showed you for optimizations, sure, we can kind of reason about that, but some later we'll see are so crazy, it's not worth your brain space to think about it. And there's a great Lord of the Rings length talk from Herb Sutter called Atomic Weapons, the C++ memory model and hardware that really is a deep dive into how you should do all this correctly and how all this works that I recommend. Another thing about we're wondering like, well, how this always work in Intel assumptions is we were doing some iOS apps and some custom hardware that was based on ARM, but a lot of that was new code and a lot of this legacy stuff was in our legacy desktop software, so they were spared a little of that until later these Apple Silicon Macs came out, and there's another story we'll get to later in the talk. But in a legacy code base, dealing with undefined behavior can feel really hopeless. Like how are we going to fix all this stuff that has been going on for 25 years in our code base that could be wrong? When I gave this talk a few years ago, this numbers might be bigger, but I just looked at the isotope code base, and we were dealing about 15 million lines of code. Most of that in open source stuff, but within our own code base in the currently shipping products, we had about 2 million lines of code. So it's like, oh, let's go fix all our undefined behavior. Like, it's a really big, long mission, and that might be tough to justify the business value of that. So you got to take it step by step. And as I said, it can feel hopeless for a number of reasons. Like I said, there's too much to fix. But there's also other attitudes you might encounter, like, well, we've been doing this for years. Why fix it now? It's totally fine. Or even on a PR, if someone's discussing undefined behavior, oh, well, this works. Why fix it? Or there's another attitude I've heard, which is that undefined behavior, this is just some intellectual topic for nerds that like the standard, but like us day-to-day developers don't need to worry about this. And if you know anyone like this, point them to my talk. No, it's not true. We should all be scared. So where we started, we had all warnings enabled, basically, and warnings as errors, so that will help us with some stuff. But we've been dreaming of static analysis in CI, and we're starting to look at running clang tidy on new code. And we were aware of the clang runtime sanitizers like address sanitizer, UB sanitizer, thread sanitizer, but we weren't using them in CI, and that was non-trivial to get running. And actually, when we were preparing this talk, we found a very old ticket in our Jira, research address sanitizer, that I don't know when it was filed, but in 2022, when we finally closed this, realizing that, oh yeah, we've implemented this, it had been open for almost 2,500 days, so you do the math on how many years that is. So, I've got some peace stories fighting undefined behavior. And as an aside, the reason I call them peace stories, the first version of my talk, these were war stories. But internally, during a product release, we decided we were in crunch time and got all the developers together with their computers in one room to kind of smash some bugs, and we were going to call it the war room. But one of my colleagues pointed out, well, no, we don't want to be violent, so let's call it the peace room instead. So these are peace stories, not war stories. And just to share two other fun things that you could maybe use, if you hear this phrase, kill two birds with one stone, the nonviolent version is feed two birds with one scone. Again, that one comes from my colleague Russell, so that's why he got the thanks. So this first one was a really fun one, the attack of the Xcode update. We had some strange stuff happening in our UI UX design when a UX designer did an automatic update to Xcode through the App Store, and we were not using that version of Xcode yet. And this is RX, our post-production audio editing software. Actually used for post-production and music, but it's used a lot in film and television stuff. And this is what the UI is supposed to look like. And when we update Xcode, it started looking like this. And I'll zoom in to show you what's wrong. These tabs, instead of being a trapezoid, are turned into this weird triangle. And all of a sudden, these radio buttons, instead of being circles, are these weird, long, cut-off ellipses. And we're like, that's strange. Maybe it's a compiler bug. So we asked for help on IRC. Someone suggested this program, C-reduce, that will, you give it some test case, and it will basically delete code until it finds the minimal thing that's causing a problem. And all the code disappeared. And so we realized, okay, maybe it's us and some undefined behavior that's going on if this happened. And so the way we dealt with it, we jokingly call this in the office UB the compiler. Essentially, my colleague Russell and I, he built it with the existing Xcode, I built it with the new one, and we were essentially, he was reading me instruction by instruction what was generated until we found one that was different. And it was weird, and we'll get into what was actually going on in a second. And then finding that instruction, we were able to pull up and then find, okay, what function is this happening in, and keep stepping up the call stack till we found the spot that we invoked some UB. One kind of learning is you didn't find a compiler bug. And if you assume you have, it's probably you. Not always. We have found one once, but usually it's not you. So don't jump to that, make our mistake of jumping to that conclusion first. So here's where the problematic code shows up. We have some code using this old code using this drawing library, AGG, also called anti-grain geometry. And we're doing a few things here. We're essentially trying to draw an ellipse at a position and with some radius, or a circle outline, but we use this ellipse function. So first, we create a ellipse at that position and radius. We create a stroke object with this. And then there's this transform that's applying some other information to kind of this X and Y is local to whatever widget you're in, and this transform will then put that in the actual position on the window. And this call to this transform returns a temporary, and that's where the problem comes in, because it's not some nice code, but in AGG, this is what the constructor for transform looks like. So it takes the transform by a constant reference, so it can bind this to a temporary, and then it takes the pointer value of that and stores it as a pointer in its object, and also as a const pointer, which has its other problems, but that's not the point here. And so this temporary is going to be gone later when we call add path and actually rasterize this. And what turns out what was happening is in the rasterizer, when it was actually applying the transform to every point in the stroke for the ellipse, instead of passing the X and Y into the apply transform function, since we were in UB land, the compiler was like, I can do whatever. So it passed X and X as the two arguments instead of X and Y. I don't know why the compiler decided to do that. Maybe it was a little more efficient to load one thing. I really can't tell you. And actually, the funny thing is, when I prepared these slides, newer versions of Xcode didn't do anything strange with this UB. So I actually had to simulate it to create those pictures. And its solution is pretty easy. Just, don't make it a temporary, store transform on the stack, and then it will survive until the end of this. So let's fast forward in time a little bit. And this is an example of when your code breaks when you didn't change it. So at this point, we have automatic clang format and clang tidy running on our code. We've adopted C++ core guidelines, but we're not really adopting ASAN and UBSAN yet, really, even though we know these tools exist. And all of a sudden, one of the products a team I was leading was working on, there was a Windows update sometime the week before we were shipping, maybe even the day before, and all of a sudden our plugin, when instantiated, would crash every time if you had the latest Windows update. It was totally fine with the old Windows and Mac. As Anthony said in his keynote yesterday, undefined behavior is often a consequence of unexpected events. This is kind of one of them, because you'll see we changed how some of the code works. And it was the most exciting day of my career fixing this before launch, because it was too late in the day to call Japan and tell them to not start marketing the product at 2 a.m. US time. So it was going out whether we wanted it to or not. And luckily we did fix it the next day. So we had a few people swarming on it, and one of the developers used Visual Studio's static code analysis. And when he ran that on the solution, it found this. We had this struct called snapshot data. I'll show you in a second what we use it for, but it's essentially storing a snapshot of some frequency analysis of some audio and some other information about how to display this on the screen. with opacity. And the snapshot color, you'll see, has no default value, which was fine in the first implementation where we used this, because it was originally when this code was written, maybe I think 5 or 6 years before I joined, we always populated that with a value. But when we're working on Ozone 9 and this match EQ function, you'll see these two yellow and orange spectrums at the bottom of the screen. That's what's being represented by that snapshot data. And we changed how we were serializing this stuff. Previously, they were saved to disk, and we changed them to be saved in the state of the audio project you're working on, because saving to disk would cause problems if you moved your project file from one computer to another, and this other random file we wrote to disk wasn't there. So we thought, oh yeah, it would be better for users if we save this within their session data. Where the problem comes up is that it's possible to have this reference on the left populated in a preset or some standard starting state, and then the apply to is the audio you want to, essentially what this is doing is taking some audio, and you say, I want to basically take the audio I have right here and kind of give it the spectral shape of the audio over here. But if you haven't captured something for this spot 2 on the right, that means we've not assigned any information to this yet, and it's just in its default state. And its default state, even though we always want it to be blue, since we've not set the frequencies or the decibels, we didn't set any of this. And so when we were saving this state with an empty apply to in slot 2 here, we were actually going to read this uninitialized snapshot value. And where the crash came in is some other code that evolved organically over the years and probably made sense at the time. And this is a simplified version of how we were saving this state. And it wasn't just a snapshot data. It's huge amounts of state for this product. This is just one piece of it. But essentially what we're doing is getting what we want to save, compressing it, and then figuring out, okay, what's the compressed size of our data? Then once we have that, we allocate some memory using that size, and then compress it again and put it into that. The reason for that developed that way is a long time ago we were not compressing the data because it was less data when these products were newer, but we started compressing it. And you'll see what will happen is when we read it the first time, and this again, we're assuming we understand undefined behavior here. Essentially, we often view, like I said, reading these ints that aren't initialized, while the compiler could do anything and just optimize away all of our code. Usually what happens is, in practice, you get a garbage value. And so the first time we compress to see the size, we might have a different value in that one spot in the data than the second time. And then those different numbers mean the compression algorithm might actually end up with a different size at the end. And coincidentally, on Mac OS and on Windows until this update, the second call was always needing less space than the size that was given. But all of a sudden, there's one Windows update, for some reason, whatever we were reading garbage data from was causing the compression to say the size was smaller than we actually needed. So the fix is really simple. Just default initialize that and no problem. And then, yes, later fix this shenanigans because there's other bugs that turns out this could cause as well that weren't undefined behavior, but just other crazy threading situations that are defined but buggy. So later we also cleaned this up, but for fixing it in a few hours before we launched, that was all we needed. Another example I'd like to talk about are non-deterministic regression test failures. So when your code breaks when you didn't change anything. So we have a library that is for doing regression tests on our signal processing code. So not the entire product, but we basically build every piece of DSP we have as an individual DLL, and we can compare a kind of gold blessed version of that with your new builds, and we check, is the output the same? And by the same, we mean within minus 100 dB decibels difference. Basically, to human ears, is it the same? Because if there's slight differences due to some math libraries we're using or other things where things change a little bit, that's fine as long as your perception of the sound is the same. It doesn't actually need to be byte the same, because humans are not going to hear a 140 decibel difference between stuff because your ears can't do that. But we had some of our tests that were failing sometimes. And people would usually just rerun them and until they went green. But at some point, I had some spare time, and I'm like, look, I want to investigate what's going on. I'm aware of using the sanitizers, so I go into Xcode. I turn on address sanitizer and ubsan, and I found the problem. And sorry, that's a duplicate slide. It's not supposed to be there. And so the problem we found is we had this utility for essentially accessing temporary memory on a real-time processing thread. So in this case, we can't actually allocate any memory. So essentially up front, all the processing code we have declares how much temporary memory it might need, and we allocate that on instantiation in this memory pool. And then we use this memory pool buffer, which is kind of like a vector, or really two-dimensional vector, that we can use to not allocate memory, but just access some of this temporary memory from this memory pool. And so we'd use it kind of something like this, where we have a memory pool, and like we might have some process function that takes some buffer as input, and so we need to create some temporary analysis buffer of that size, so we get that size, and make this analysis buffer with the memory pool. We do our analyze. Maybe we need some other calculation buffer, so we create that, do this calculation, some other stuff. And so what's going on here is the first time we create this analysis buffer in the memory pool, we're asking for 512 floats, let's say, as an example. And so we might get a range that goes from that address to CEBF40 to CEC740. And then the next temporary memory we create is going to start at the next byte in our memory pool. So we'll start at CEBF40, and it will go to CED740. And this is all groovy. But what if we're not using power of 2 sizes for our temporary memory? So sometimes, like imagining you're doing a real Fourier analysis, the way this would work is we'd want essentially the buffer size divided by 2 plus 1 for our analysis. And so now we're no longer in power of 2 sizes. And so what happens here, you notice we don't have these zeros at the end anymore for the end of our first range and the start of the second one. And so what this means is that when we create this calc buffer, it's a buffer of doubles, but it no longer has the correct alignment to read those doubles. It's at a 4 byte offset of where it needs to be. And ASAN just told me that's the problem. And then I added some extra code to make sure things are always aligned for the types you need. And all of a sudden, all these non-deterministic DSP failures we were seeing in our regression tests went away because of this. And again, how did this ever work? What was going wrong? Because an Intel CPU, as far as I'm aware, can read things from unaligned addresses, but C++ says you can't. So was it something in the compiler doing something weird? We also use the accelerate library for doing vectorized math operations on Apple, and the IPP library for doing this on Windows. Were those libraries expecting alignment and doing something strange? If not, I don't know. And this is another example. This is a good example. My point of it's really not worth trying to understand what was going wrong here. Just knowing that it was wrong, and you're not allowed to do it. So don't do it, and don't try thinking about it too hard. Just use the tools, have them tell you your code's incorrect, and please fix it. So seeing some of those scary examples, we really wanted to make some cultural and tooling changes to start making sure we didn't write new code like this and slowly remove undefined behavior from our code base, and without dealing with kind of all this, how do I say it, discouragement of trying to do that to a 25-year-old code base. So what did we do for cultural changes? First was fear-mongering. Scared everyone about how scary non-deterministic build failures are, and like never rerun, never rerun. If it's sometimes red, sometimes green, that's even scarier than red. Please investigate. The other one was we started reprioritizing bugs that might have seemed like a low priority bug if they smelled like undefined behavior. We could maybe do that a little bit more. That's maybe a discussion for the hallway. Like, is that really worth calling something high if you guess your code is wrong and you don't have proof? Another one is education and teaching everyone at the company, not just developers, about undefined behavior and why C++ is difficult and why we should care about this. And we made a new rule that you're not allowed to write undefined behavior. So I said fear-mongering. One, I just started scaring shared these stories and basically telling the other developers on my team, please, 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 if you see a red build and you rerun and it goes green, it's not okay to merge your PR. Maybe something is actually wrong, so please look into this. This was a really interesting bug, and this is what started making me think about influencing bug triage. This is just some properties on a product analytics, behavioral analytics event that we had. And you notice this primary classifier, this is essentially deciding like if we're, had some genre classifications, so doing some, giving you some intelligent suggestions on your mastering settings based on what we detected your genre is and what we might think we could do with that. And we were getting this garbage data in there. And we were triaging bugs. The product manager said like, oh, well, we're not actually using this metric at the moment for anything, so I don't really care that we're not getting good data out of this. But when I saw this, like, I mean, those are the Unicode question marks, so that isn't even valid Unicode. Like, clearly, we're reading some garbage data here and putting this into this property. And I realized, well, okay, I told my colleague, hey, Dan, you might not care that you have this garbage data, but what about all the times where this didn't crash? And someone might have been reading garbage data and we actually, crash in this case. So this might seem fine for all the analytics we get, but we don't know, could this be causing crashes for every bogus event we've not gotten? And so trying to encourage developers to, if something seems like the bug on its own in isolation isn't high priority for the business, if it gives you the hint that there's something wrong in our core libraries, it still might be worth taking a look at. And then the one that inspired me to start actually teaching the rest of the company and not just developers about undefined behavior is at some point in Slack, I think we were discussing a bug and one of the developers might have said UB somewhere, and one of our QA engineers comes up to me and says, hey Roth, what's an UB? And we now do affectionately call them UBs sometimes. And so I explained to him what it was, and that's what inspired me to start teaching QA and the rest of the company about this. So I actually gave an internal tech talk called Battling Dragons in Ozone that was the story of that launch day crash. Because customer care was involved, they had to sign off on are they okay dealing with this if we can't fix it in 24 hours, et cetera. So the whole company knew the kind of challenges and scary stuff that can happen working with legacy C++ and undefined behavior. The other thing we did is we have a fork of the core guidelines. We removed a couple that don't apply to us. In our code base, we're not using exceptions, so we didn't need some of that stuff. We also added some of our own guidelines and things that are specific to our code base. And we made a rule, do not invoke undefined behavior. This came up because sometimes on PRs, someone would point out, oh, you really can't use reinterpret cast or union type punning this way. It's undefined behavior. You need to use memcopy. Or other things someone might point out undefined behavior on a PR. But someone would say, well, it's already been QA'd. This works. What's the problem? Why can't I do this? But our philosophy with the core guidelines is those are not up for debate. If we have this in the core guideline and you can quote a core guideline on a code review, it's just okay, please address this. Unless, of course, it's one of the enforcement exceptions. And so once we had this rule, do not invoke undefined behavior, it was no longer a code review discussion. If someone noticed UB somewhere, we just committed we had to fix this. And the idea is that even if we have UB in our code base, that doesn't mean we have to make it worse. And our new code, we should strive to not have undefined behavior. And we want to reduce cross-platform breaks, and we want more devs watching out for UB in code review. When I gave this talk in 2022, I got a question afterwards. Hey, why isn't that part of the upstream core guidelines? I didn't have a good answer. I figured it was probably assumed to be table stakes by the people working on that and not even mentioned. But in preparing for this talk, I actually opened this afternoon PR to propose having a don't write undefined behavior guideline. If you feel strongly, here's a QR code about it. You can go discuss. I just copied our internal wording, which might not be the best, but mostly to see, I'm kind of curious. I haven't checked yet if after the talk there's any feedback on, are they open to this suggestion or not. Whether it goes in the core guidelines, I recommend you don't write undefined behavior. And then we made some tooling changes. we built some technology so that normally our deprecation warnings were not warnings as errors, but we were able to make in CI for only new code that warnings as errors, deprecation warnings would actually be errors. So if we deprecated anything that was old, specifically we knew that function had UB, you couldn't use it in new code. We started also using clang tidy, again, only on new code, because our whole code base, that would not really be tractable. And we also used clang tidy to do some refactorings. And then we also started doing CI builds with address sanitizer and UB sanitizer and manual use of thread sanitizer. The reason we're using thread sanitizer manually is for the other sanitizers, we started with unit tests, and most of our unit tests were single-threaded, so tsan wouldn't help us there. And also, you need 2 builds to do that as well. So an example of why we want deprecation warnings in new code is we had this param registration function that took a raw pointer to some type, like a float or bool or an enum parameter. And it's more complicated than this, but essentially the issue was, it turned out way under the hood, the way our lock-free queue was working, we didn't realize that actually was a race condition accessing those members that we were passing in. So we realized we actually had to be using atomics for the memory for these parameters we'd register. And the point here is we were able to write this new overload that you must use in new code. And the reason we didn't just fix all of this immediately is there's 200 DSP repos that were calling this poor API, and it seemed to be working. So like we couldn't just fix it all, right, drop everything and fix it. So new code has to use this, and then with this deprecation warning, old code can never call the UB function because it will fail a CI build. And actually old code, if you touch it at all, will also fail the CI build and force you to motivate it. Also, like I said, using clang tidy. So this is static analysis. It has many built-in checks. I said it's not hard to write custom checks, and I showed an example, but it's not easy either. And so if it was easy, we would have written more custom checks. And it's also a critical tool for helping to prevent some UB, because it will warn you about some things that it can analyze at compile time, like use after move sometimes, and other things like this. And it can help with automatic refactoring. I'm kind of going to breeze through this part a little bit, but we had just a small example how I can use it for fixing bugs and not UB with automatic refactoring. We had our kind of own version of an optional, and you'll see instead of like a standard optional that is either has a value or doesn't, this one only worked with default constructible types. So even when it didn't have a value, you can actually still get a default value out of it. So what could happen is it had a conversion operator. So if you just assign this our kind of legacy optional of a float to a float, it would just give you 0 if it was invalid, which might be the thought at the time. It's like, oh, well, 0 will work fine. But actually, depending on your use case, 0 might not be UB, but it could cause a bug. If it's an index into something, maybe that actually could be UB if you're doing some offsets, who knows. But we have this safer one that has a cast with an assertion, so at least you know, like you really shouldn't be unwrapping that. And so we were able to write a clang tidy check, where this is an example where in case this checked int x is coming in an invalid state, we actually want to call .cast to have an assertion here. And so if you want to look at this code later, I'll share the slides. This is a check that looks for that, and we apply this fix it, so we were actually able to fix that all over our code base as well. So not UB, but another kind of advocacy for tooling to help you write C++ better. And then the really big one was actually starting to roll out address sanitizer and UB sanitizer to our code base. So these are runtime checks for various forms of UB. And we started running it on all of our project's standard unit tests. And we recommend you make a plan for rolling this out and not assuming you do it everywhere. And do it one step at a time. Because every time you might open this PR that enables these sanitizers in one library, all your tests might pass with the sanitizers and be great. Or you could have bugs to fix, and so you couldn't enable this over the whole code base, but one library at a time, and then moving up the testing pyramid as well. And if you're not familiar with this, I'll mention the testing pyramid in a moment. And also, just a caveat, on Mac OS, when you use this, you might need to inject some environment variables to find libraries that make these sanitizers work. And so one of the things it found is actually an example, as I mentioned earlier, about using reinterpret cast when you're not supposed to change types. And so this example was flagged when we started rolling this out in unit tests somewhere. And so we were able to fix this by using memcopy to do it the kind of appropriate way. Bitcast, I think, would work here as well in the future. And then, as I mentioned, here's kind of an example of what you need to do. Is basically there's a ASAN and UBSAN library that needs to be used at runtime on Mac OS, and so you insert that with this dealyd insert libraries function. It's a little bit trickier in modern OSs, so if you ever have any questions about that, you want to reach out to me. We have lots of experience working around the issues with this. As I said, you want to roll this out step by step in your code base. And so we started with unit tests, and then the testing pyramid is integration tests, and then you have end-to-end tests as your kind of highest level, but maybe most brittle tests. And for us, what that means is we have unit tests, we have these DSP regression tests that I mentioned earlier, and then we have end-to-end tests, so we're actually loading our entire DLL and exercising the full plugin. And so initially, when I first gave the last version of this talk, we were still in the process of rolling it out for unit tests. We've done that everywhere now, and actually our test automation team has done a lot of great work to make our tooling for the other two levels of the pyramid also support the sanitizers. And so the teams are now deciding their plan to roll that out for the rest of our test coverage, which will be really great. The one downside is that this has these will not help you if you don't have code that will exercise your tests. So, enabling for all your tests is one thing, and then finding when you see bugs or the UB where you need actually more test coverage to exercise your code more with these sanitizers. And as I said at the beginning, you're talking about legacy Intel assumptions. I remember actually when I started ISO talking with colleagues about some of this works on Intel stuff we have in our code base. And it's like, yeah, but we make iOS apps. It's like, oh yeah, but we don't use any of this. We're never going to use this library on iOS, so it's not a problem. But then Apple releases Apple Silicon, and now we have ARM, and even this stuff that supposedly works on Intel, although we saw maybe not always, all bets are maybe off with ARM and some of this stuff. So we decided instead of starting with manual QA and just looking for bugs on ARM, that might be a waste of human effort. So we wanted to instead start with using Thread Sanitizer to smoke out any of the issues that might exist in our code base first, before we handed it off to manual QA to qualify this stuff that our products work in Apple Silicon. So again, this is another runtime sanitizer. For various reasons I don't fully understand, not all sanitizers can run together. So ASAN and UBSAN can work in one build, TSAN cannot. Like I said, we're running this manually because most of our unit tests were not single-threaded. And we found many threading bugs, like that register param one I mentioned earlier. But we also did waste some dev cycles for developers that were less, familiar with, threading and C++ stuff, finding false positives when they're running this tool. Like, for example, we're using this library for lock-free reader writer queue from Moody Camel, and there's false positives in this library that needed workarounds because I think some stuff with atomic thread fence can sometimes confuse thread sanitizer. And these links here show some issues and commits on how to do that workaround if you're curious. But doing all that stuff, we were now happy on Apple Silicon and our products work great. And also, we seem to make a bug go away that in our worked on Intel era somehow. So there was many bugs in our implementation of the frameworks that allow our plugins to talk with host audio applications. And you'll see here what this QA is reporting is these are lines for automating some parameter, like recording what moves he's doing with the mouse. And you'll see it's not a smooth line that's happening, but all this kind of jagged, crazy stuff that's going on. And we noticed, we would see this sometimes in our products, and we did not know why. And after we did the big pass with Thread Sanitizer, I asked our QAs, hey, have you ever seen this bug again? And the answer was no, it seemed to go away. And again, don't try to understand it all, but this is a nice effect of making the effort to use Thread Sanitizer to purge a lot of these threading issues. Mystery bugs in our backlog just didn't appear anymore. I also want to tell you about one recent surprise that showed up, and I'm not sure if this was from UBSAN or was from new warnings in a Clang version, but when a developer was up, because the commit message was very short on this git blame line, so I don't remember exactly what was found, but there was an issue we ran into using standard sort, because the contract of standard sort is that the left side and right side that are being compared, you return true if A is strictly less than B. But in this case, I wrote it less than or equal to. In practice, everywhere we use this in our code, the sort actually worked out correctly. But this was actually flagged as, no, this isn't a strict ordering when you do this. The correct code is to use less than here. And so we fixed this to work around whatever. Like I said, I wish it was in the commit log to know, but where I found this. But then about a month or so later, I was talking actually with my colleague Russell, who I don't work with anymore, but a different code base he's in. And he was telling me, oh, Roth, you wouldn't believe this weird bug we found. It was using less than or equal to in a sort as comparison. And it actually caused them a bug. And I was like, oh yeah, we actually just saw this in our code base too, flagged by Xcode. So that was just a little fun bit of new material since the last time I spoke about this I wanted to add. And then I'd like to close here and save time for questions. But if you want an extra fun story in the hallway, I can tell you about an example where in our software, constcast changed the meaning of silence, where silence wasn't silence anymore. So thank you very much. What are your questions?
If you discover a UB example or a place where it happens, is it practical for your code base to do a grep for similar things, or did you say, nah, it doesn't work because there's 1,000 invocations of sort, for instance?
Yeah, in general, I have not done that. I think it's probably better to just incrementally roll these tools out across your code base. Or, although actually I hadn't thought about this, but it actually would be, like I said, I don't remember if the sort example was actually a new warning or if it was a new UBSAN feature, but for things that are flagged by like UBSAN, if there is some way to grep for parts of your code base for that and find that there's not test coverage, that might be good place, like hints to where you need to add more test coverage. But yeah, so far that hasn't been our approach. It's more just been roll this out more places and just try to increase test coverage in general until things are flagged. But it can't hurt to try that. But grepping C++ is always a tricky concept. But yeah, I hadn't really thought about that too much, so thank you. Well, if there's no other questions, then we do have a couple minutes. I can tell you my...
Is this a new question? Nope.
I can tell you the quick constcast story. So there's one audio editing piece of software called Pro Tools, and it has all the different kind of... There's a number of different kind of APIs and SDKs for making audio plugins that run in either audio editing or video editing software. And Pro Tools has its own proprietary API called AX. And the way that works, some of these plugin processing APIs will make you implement a process function that does in-place processing. So it gives you a buffer that's your input, and then you write your output to the same buffer. Other APIs will give you a buffer as input and an output buffer you're supposed to write to. And in Pro Tools, technically that API is they give you input and output buffer, and the input buffer is a pointer to like const floats, and the output buffer is a pointer to floats. And in practice, normally, they were pointers to the same memory, and it was an in-place operation. So we were casting away the const on the input and just doing it in place on the input buffer because all of our processing was designed to be in place. But it turned out Pro Tools, when there wasn't audio on the track that was feeding your plugin, and there was just like no audio data, instead of just feeding you just arbitrary zeros, they had their own internal silence buffer that they would use. And that might have been just for optimization, and it was just zeros, or it might have been actually a little dither and not zeros that it was. But when we constcast that away, and we're doing this in-place processing, every time our plugin was called, we would change the data that was in the silence buffer, and slowly over time, the silence buffer was getting Yeah, less and less silence. And so in that case, like I said, in most cases where we were being called, the casting away const was safe. Because if you read const cast, it's like you're allowed to do a const cast and cast away const only if the original object is not const. And so we knew in the standard case that was true, and so we could get away with it. But in the silence buffer case, it actually also, like, from a language standpoint, wasn't const, but it was more just an API contract thing where, please don't touch this. So, yeah, just don't use const cast, please. So that's it. Thank you very much. Oh, is there another question, please? Yes.
So it seems you can openly speak about the errors in your company. Did you have any issue with marketing or something to get the allowance to do that publicly?
Well, there's two pieces to that question. In general, what we consider, like what we shouldn't talk about in public is like our proprietary DSP and machine learning stuff that we do. Talking about this stuff is, not normally considered a big deal, but also I'm kind of lucky in my current position. I'm the one that gives feedback to other developers on what they should talk about publicly. So I'm in charge of deciding this stuff, so I get to pick about what goes in my talks, and no one has, none of our CTOs have been upset with me yet. So yes. And actually, I really like talking about our. In my talk tomorrow about leadership stuff, bragging about failure is one of the themes. So I really like doing this in general. And also, I feel like these stories are really useful for other developers who hear them to come back to their teams. And because I met developers who've seen like my past version of this talk who will tell me that, oh, wow, I really want to take this back to my team because I'm dealing with the same issue of pointing out undefined behavior and people saying like, oh, no, you're just some standards nerd, like this doesn't matter. And so I feel like these concrete examples are, useful for, helping all of us in the community, help all of the other developers know, how scary this stuff can be. Yes, please.
One more short question. You added a rule to don't write undefined behavior. Isn't that the same to say to developers don't write bugs? How does it get enforced? So usually you don't experience that it is undefined behavior until you change platform or migrate it to somewhere.
Yeah, so there's a couple kinds of things you can run into with undefined behavior. Like the divide by zero example we were looking at before. Like, yeah, you could change your code and all of a sudden now you're dividing by zero. But there's other things you can do that are always undefined behavior. Like type punting through a union is always undefined in C++. And so as far as enforcement, unfortunately, it's not a guideline you can necessarily statically enforce unless you can runtime enforce it with UBSAN. But it's more... we use the core guidelines as essentially the topics that are not for discussion on PRs. So the point was that if someone notices something that is always going to invoke undefined behavior or could potentially invoke it, there's no debate on the PR if you fix it or not. So it's not really an enforcement thing. It's more a cultural enforcement saying we've all agreed we don't intentionally write code that invokes undefined behavior or could invoke undefined behavior. Of course, whether it's LLMs or humans, we are both, no one is perfect at writing C++. So that guideline has not always been followed and and using UBSAN has helped us fix some bugs right before release a number of times, including a couple years ago. I was actually asked to help out fix a bug with a team. And it turned out it was actually some UB I wrote. And no one would see this in the code review because it was way a team effort between me and a third-party library. But once, and it existed for probably 6 years in the code base, and then was causing a crash in one product when they did this one thing, open a bit of our UI. But with UBSAN enabled, as soon as I clicked that part of the UI, it told me, oh, this memory is no longer this object's no longer valid over here, and then I realized, oh, there was some state that should have been cleaned up when we removed something from the UI and put it back, and that didn't happen. So, you can. Yeah, I don't know if that answers the question, but
right, we're exactly on time.
Thank you very much.